Nestled in Fort Worth, Texas, U.S. Air Force Plant 4 is one of the most consequential pieces of real estate in the entire history of military aviation. Spanning approximately 3 square kilometers, roughly the same footprint as New York City's iconic Central Park, this sprawling complex is the birthplace of the most technologically sophisticated combat aircraft ever to take flight. The facility is operated by Lockheed Martin, the American aerospace and defense giant that consistently ranks as the largest defense contractor in the world by revenue, pulling in over $65 billion annually. It was no small feat gaining access to this place. Securing permission to film inside took 2 full years of negotiations, approvals, and background checks. The security apparatus here is formidable. Multiple layers of credentialing, armed personnel, and access restrictions that escalate from confidential all the way up to top secret. Simply put, most people will never set foot inside these walls. The aircraft that rolls off this production line is the F-35 Lightning II, a single-engine, supersonic, multi-role stealth fighter that represents the pinnacle of what human engineering and military investment can achieve. The program, formerly known as the Joint Strike Fighter Program, is the most expensive weapons system in history, with total life cycle costs estimated at well over $1.7 trillion. 13 nations currently operate or have committed to acquiring the F-35, making it not just an American asset but a cornerstone of NATO and Allied air power for the next several decades. The production line. The manufacturing floor at Plant 4 is a sight that stops you in your tracks, stretching over a mile in length, comparable to the full span of the Brooklyn Bridge, or 17 soccer fields laid end to end. The production line is a cathedral of industrial precision. On both sides of this massive corridor, F-35s in various stages of assembly stand in organized sequence, each one a work in progress being slowly transformed from raw structural components into a fully operational war machine. At any given time, over 100 fighter jets occupy this line simultaneously. The workforce required to sustain this operation is staggering. More than 18,000 people are employed here, 3 times the population of an average American small town. These aren't just assembly workers, they include aerospace engineers, materials scientists, software developers, quality assurance specialists, logistics coordinators, and dozens of other specialized professionals. Together, they collectively represent one of the most skilled manufacturing workforces on the planet. This site has a storied history that predates the F-35 by many decades. Production here began during the Second World War in 1942 with the B-24 Liberator, a 4-engine heavy bomber that played a critical role in the Allied bombing campaigns over Europe and the Pacific. The facility subsequently produced the B-32 Dominator, the massive B-36 Peacemaker, which had a wingspan of 70 meters and was the largest mass-produced piston-engine aircraft in history, the experimental XP-58 Chain Lightning, and later the F-111 Aardvark, a revolutionary variable sweep-wing aircraft. In the modern era came the F-16 Fighting Falcon, one of the most successful and widely exported fighter jets ever built, and the F-22 Raptor, widely considered the world's most capable air superiority fighter. Since 2004, the F-35 has been the centerpiece of production. 3 variants of the F-35. The F-35 program is unique in that it encompasses 3 distinct variants, each engineered for a different operational environment, yet sharing approximately 80% of their components, a deliberate design choice that dramatically reduces long-term maintenance and logistics costs. The F-35A is the conventional takeoff and landing variant, designed for traditional Air Force runways. It is the most numerous of the 3 variants and carries an internal 25mm GAU-22/ rotary cannon, making it the only variant with an internally mounted gun as standard. It is also the lightest and most agile of the 3. The F-35B is arguably the most technically remarkable. It features a short takeoff and vertical landing capability, meaning it can take off from extremely short runways and land vertically much like a helicopter using a revolutionary lift fan system developed by Rolls-Royce and a rotating nozzle at the rear of the engine. This variant is operated by the US Marine Corps and the UK's Royal Navy and Royal Air Force, among others, and is designed to operate from smaller amphibious assault ships and austere forward operating bases. The F-35C is the carrier variant, built for catapult launches and arrested landings on full-size aircraft carriers. It features significantly larger wings than the other two variants, increasing fuel capacity and lift, as well as reinforced landing gear capable of withstanding the extreme forces involved in carrier deck landings, and a larger tailhook for catching the arresting wire. The Metrology Lab, precision at the microscopic level. One of the first stops inside the facility is the Metrology Lab, a place where the science of measurement reaches an almost philosophical level of obsession. It is important not to confuse metrology with meteorology. Metrology is the scientific study of measurement, and in the context of the F-35, it is utterly critical. When you are building an aircraft that must maintain a precise radar cross-section, fly at twice the speed of sound, and withstand forces 9 times the pull of gravity, the tolerance for error is essentially zero. On a workbench lies an actual panel from the F-35's underbelly, a piece of the outer skin that very few people outside of Lockheed Martin's engineering team ever get to touch. Looking closely at this panel, one notices the thousands of fasteners holding it in place. Each F-35 contains exactly 40,000 of these fasteners in total. Each one must be seated to exact specifications, because a misaligned fastener doesn't just create a structural weakness, it can compromise the aircraft's stealth profile by creating surface irregularities that scatter radar waves in unpredictable ways. The team here uses sophisticated 3D laser scanning technology to digitize panels and structural components, ensuring that every piece fits within tolerances measured in thousandths of an inch. Alongside this, they employ a technique involving a special photosensitive gel that, when applied to a surface and illuminated, reveals scratches, dust particles, and micro-imperfections completely invisible to the naked eye. This level of inspection might seem excessive until you consider what's at stake. A microscopic flaw in the aircraft's skin could compromise its stealth coating, making it more detectable to radar. For structural defects beneath the surface, the team uses ultrasonic scanning technology, essentially the same principle as a medical ultrasound. The F-35 makes extensive use of carbon fiber composite materials, which are significantly lighter and stronger than aluminum but can develop internal delamination or micro-cracking that is completely invisible externally. The ultrasonic scanner is pressed gently against the surface and sends sound waves into the material. Inconsistencies in how those waves bounce back reveal damage inside the composite layers that would otherwise go entirely undetected. There is also a robotics element to the lab involving transponder-based coordinate systems robots programmed to perform inspections or manipulations using sensor fusion to understand their precise position relative to the aircraft in three-dimensional space. It is a fitting preview of the kind of human-machine collaboration that defines the F-35 program at every level. The F-35, a technical marvel explained. Before diving into the human element of the program, it is worth pausing to appreciate just how revolutionary the F-35 is from a purely technical standpoint. Stealth is the aircraft's most celebrated characteristic, but it is often misunderstood. Stealth does not mean invisible, it means having a radar cross-section so small that radar systems either cannot detect the aircraft at all, or detect it so briefly and at such short range that it is effectively useless for targeting. The F-35's radar cross-section is approximately 0.005 square meters, roughly the size of a metal golf ball. To put that in context, a human being has a radar cross-section of about 1 square meter, and a bird registers at approximately 0.01 square meters. The F-35 is 5 times harder to detect than a bird in flight. This is achieved through a combination of carefully shaped surfaces designed to deflect radar energy away from the emitting source, radar-absorbent materials embedded into the aircraft's skin and structure, and internal weapons bays that keep missiles and bombs hidden inside the fuselage rather than hanging from external pylons. The radar-absorbent coating on the aircraft's exterior is one of its most classified features. What is publicly known is that it is a specially formulated paint-like substance containing materials capable of absorbing rather than reflecting electromagnetic radiation. The precise chemical composition and application process are classified at the highest levels, but the general principle involves the use of ferrite-based compounds or similar materials that convert radar energy into heat rather than reflecting it back to the source. Maintaining this coating is one of the most labor-intensive aspects of F-35 operations. Even minor scuffs or chips need to be repaired with exacting care to preserve the aircraft's stealth characteristics. Speed is another defining feature. The F-35 is capable of reaching speeds of approximately Mach 1.6 around 2,000 km per hour in level flight, and can sustain supersonic speeds without using afterburner, a capability known as supercruise, though this is more associated with the F-22. The afterburner, which injects raw fuel directly into the exhaust stream for a massive but fuel-intensive boost in thrust, pushes the engine to its maximum output of approximately 43,000 pounds of thrust. At that level of thrust, the aircraft accelerates with a physicality that pilots describe as being essentially strapped to a rocket. Sensor fusion is arguably the most transformative capability the F-35 brings to modern warfare. Previous generation fighters like the F-16 required pilots to manually cross-reference multiple separate sensor systems: radar, infrared sensors, electronic warfare systems, and synthesize that information themselves, in real time, while simultaneously flying the aircraft and managing weapons. The F-35's mission systems computer does this automatically, fusing data from all onboard and off-board sensors into a single, coherent, prioritized tactical picture presented to the pilot. The aircraft essentially tells the pilot what is happening around them, where the threats are, and what to do about it. This dramatically reduces cognitive load and allows pilots to focus on decision-making rather than information processing. The AN/APG-81 AESA radar, active electronically scanned array, in the nose is a key component of this system. Unlike older mechanically scanned radars, which physically move a single antenna to scan different directions, the AESA radar uses thousands of tiny transmit/receive modules that can be electronically steered in microseconds. This allows it to simultaneously perform multiple radar functions: air-to-air search, air-to-ground targeting, electronic warfare without any moving parts, making it far more reliable and far harder for enemy systems to detect or jam. The different color of the nose section compared to the rest of the airframe is a result of the nose cone, called the radome, being made from a radar transparent material to allow the AESA radar to function, while the rest of the fuselage is covered in radar absorbent material. Weapons capacity is substantial despite the stealth-imposed constraint of internal carriage. In full stealth configuration, the F-35 carries weapons internally to avoid compromising its radar cross-section. The internal weapons base can accommodate up to approximately 8,000 pounds, around 3,600 kilograms, of ordnance, including AIM-120 AMRAAM air-to-air missiles, AIM-9X Sidewinder short-range missiles, Joint Direct Attack Munitions, JDAMs, small-diameter bombs, and other precision-guided weapons. When stealth is less critical, the aircraft can also carry weapons on external pylons, increasing total payload to over 18,000 pounds, though this significantly increases its radar signature. Meeting Siren, the only female F-35 test pilot at Lockheed Martin. The human heart of this story is found in the equipment room, the pilot-ready room where Lockheed Martin's test pilots gear up for flights. It is here that we meet a pilot whose call sign is Siren. Call signs in military aviation are a tradition unto themselves. They are assigned to pilots by their peers, often based on an embarrassing incident, a personality trait, or a memorable moment in training. In Siren's case, her tendency to accidentally set off fire alarms and police sirens earned her the name permanently. Siren's position is extraordinary by any measure. She is one of only 14 Lockheed Martin test pilots who fly the F-35, and she is the only woman among them. This is not a role achieved easily or quickly. Her path began at the United States Air Force Academy in Colorado Springs, a highly competitive military university that accepts only a fraction of applicants, where she earned a degree in astronautical engineering while simultaneously undergoing the rigorous physical and leadership training required of all cadets. Astronautical engineering, which deals with the design and operation of spacecraft and aircraft operating outside the atmosphere, is one of the most demanding technical disciplines in existence. Upon graduation, she competed for a pilot training slot, a process that is intensely competitive, based on academic performance, physical fitness, aptitude testing, and performance evaluations throughout each phase of training. Pilot training itself lasts approximately 1 year and encompasses everything from basic aircraft handling through advanced tactical flying. Those who excel get to choose from the most desirable aircraft assignments. Those who excel most get to fly fighters. From there, the path to becoming a test pilot, arguably the most elite tier of military aviation, requires additional years of operational flying experience, followed in many cases by attendance at a test pilot school such as the U.S. Air Force Test Pilot School at Edwards Air Force Base. Test pilots are not simply very good at flying. They are required to rigorously evaluate new aircraft and systems, identify problems, document their findings with scientific precision, and in many cases fly experimental profiles that push aircraft to the edges of their design performance envelopes. They must be equal parts aviator, engineer, and scientist. Also encountered in the ready room is a pilot with the call sign Seeker, a veteran F-16 pilot who holds more F-16 flight hours at Lockheed Martin than any other pilot, an extraordinary 6,000 hours. For context, the average military pilot accumulates somewhere between 200 and 300 flight hours per year. 6,000 hours represents over 2 full decades of flying at that rate. His anecdote about a close call during a combat mission in the Middle East, descending too low in a sandstorm, coming perilously close to the ground with compromised altimeter readings, offers a stark reminder that even the most experienced pilots operate in an environment where the margin for error is vanishingly thin. Learning to fly the unflyable. Before any civilian gets near an actual F-35 cockpit and given the security protocols, no civilian is going to get into an actual F-35 cockpit. There is the simulator. The F-35 full mission simulator is a sophisticated replica of the actual cockpit, with all the same displays, controls, and systems behavior modeled with extraordinary fidelity. Airlines and military services worldwide use simulators because they are cost-effective, risk-free ways to build and maintain pilot proficiency, and the F-35 simulator is among the most advanced in existence. Inside the simulator, the central controls are the stick and throttle, collectively known in military aviation as HOTAS, or hands-on throttle and stick. The principle behind HOTAS is that a pilot should be able to access every critical function, weapons, radar, communications, defensive systems, without ever removing their hands from the primary flight controls. This is crucial in a high-speed combat environment where taking your hand off the stick for even a fraction of a second can mean the difference between life and death. Every button, switch, and hat switch on the stick and throttle controls multiple functions depending on context, requiring extensive memorization and practice to master instinctively. The throttle functions essentially as a gas pedal: push it forward to accelerate, pull it back to slow down. At the far forward position of the throttle is the afterburner zone. Pushing into afterburner dramatically increases thrust but consumes fuel at a rate roughly 4 times higher than normal operation, making it a resource to be used judiciously. The G-force figures achievable in the simulator are staggering. Pulling the stick straight back while at speed can subject the pilot to 7 or 8 times the force of gravity. At 7G, a pilot who weighs 80 kilograms is effectively being crushed by a force equivalent to 560 kilograms pressing down on them. Blood is forced away from the brain toward the lower body, causing the characteristic tunnel vision, the progressive narrowing of visual field that precedes G-induced loss of consciousness, or GLOC. The weapons employment in the simulator mirrors real combat operations with remarkable fidelity. Target acquisition is performed through a combination of radar returns, infrared tracking, and helmet cueing. The pilot literally looks at a target with their helmet-mounted display, and the aircraft system slave the targeting to wherever the pilot's gaze is directed. Locking a target brings up a distinctive square on the heads-up display, and when the weapon release button is pressed, the sequence of events that follows doors opening, weapon release, doors closing takes a fraction of a second. In that brief window, the aircraft's radar cross-section increases slightly before returning to its stealth baseline. The helmet, a $250,000 piece of wearable technology. No discussion of the F-35 would be complete without a dedicated examination of the helmet. Officially designated the Generation 3 Helmet-Mounted Display System, Gen 3 HMDS, and manufactured by Elbit Systems of America and Rockwell Collins, the F-35 helmet is quite simply the most sophisticated piece of wearable technology ever produced for operational use. Each helmet costs approximately $250,000, comparable to the purchase price of a Lamborghini Huracan, and is custom fabricated for each individual pilot over a 2-day process that begins with a comprehensive 3D scan of the pilot's head. This level of customization is not cosmetic indulgence. The helmet must fit with absolute precision because it functions as a critical sensor and weapons employment tool. The helmet's visor projects a full suite of flight and tactical data: airspeed, altitude, heading, weapon status, radar returns, threat warnings directly onto the pilot's line of sight, meaning the pilot never needs to look down at instruments to access essential information. This concept, known as a head-up display, has been standard in fighter aircraft for decades, but the F-35 helmet takes it to an entirely different level by making it fully three-dimensional and helmet-slaved rather than fixed to the aircraft's center line. Most remarkably, the helmet is connected to an array of 6 external cameras distributed around the F-35's fuselage, creating a complete 360-degree panoramic view around the aircraft. When a pilot looks down through the floor of the cockpit, they are actually seeing a real-time composite image from the cameras below the aircraft, the sensation of effectively seeing through the jet structure. Look to the side, and the cameras on that side of the fuselage feed the view into the visor. This system, known as the Distributed Aperture System, DAS, means that the F-35 pilot has complete situational awareness in all directions simultaneously, something impossible in any previous aircraft. An enemy fighter attempting to sneak up from behind, a surface-to-air missile launching from the ground below, a friendly aircraft approaching from the side, all appear in the pilot's visor regardless of which direction they are physically looking. The G-suit, engineering against human limits. Alongside the helmet, the pilot wears a G-suit. The human body has firm physiological limits when it comes to tolerating gravitational forces. An untrained person will generally begin to experience tunnel vision and cognitive impairment at around 4 to 5 G, the same level experienced on a vigorous roller coaster. Loss of consciousness typically follows at around 5 to 7 G without any countermeasures. The F-35, however, is capable of sustained 9G maneuvers. At 9G, every kilogram of a pilot's body effectively weighs 9 kilograms. The heart, which struggles to pump blood uphill even at 1G, faces the near impossible task of forcing blood up to the brain against a force that is essentially pinning all fluids to the lower body. Without intervention, GLOC would be nearly inevitable at the F-35's maximum G loading. The G-suit addresses this through a beautifully simple mechanical principle. Built into the legs and abdomen of the suit are inflatable bladders connected to the aircraft's pneumatic system. As the aircraft's flight computers detect increasing G loads, they automatically pressurize these bladders, which inflate around the pilot's legs and abdomen. This external pressure prevents blood from pooling in the lower extremities and helps force it back toward the brain and heart. The suit provides approximately 1 to 1.5 G of additional tolerance, buying crucial seconds for the pilot to complete a high G maneuver without losing consciousness. Pilots are also trained to perform the AGSM, tensing the leg and abdominal muscles in coordination with the suit's inflation to further resist blood pooling. The complete flight kit G-suit, flight suit, oxygen mask, helmet, and associated connectors weighs approximately 20 to 25 pounds. This might seem manageable on the ground, but at 9G, that helmet alone effectively presses down on the pilot's neck with a force of 45 pounds, a significant cervical spine loading that makes high-G maneuvering physically exhausting even for supremely fit individuals. Preparing for a real mission. The final act of the day involves watching Siren prepare for an actual F-35 flight, not in a simulator, but in the real aircraft. Her description of the pre-flight ritual offers a window into the extraordinary mental and physical demands of this profession. The preparation is both physical and psychological. Approaching the jet, a pilot must simultaneously manage extreme focus on mission parameters, emergency procedures, weapons employment profiles, threat assessments, contingency planning, while also performing a methodical external walkthrough of the aircraft, inspecting every surface, every door, every fastener for anything anomalous. The relationship with the maintenance crew, called maintainers, is critical. These are the men and women who have prepared the aircraft for flight, know its recent maintenance history, and can flag any concerns before the pilot climbs in. A fighter pilot who dismisses or ignores their maintainers is a dangerous pilot. Once the helmet goes on, as Siren describes it, the psychological transition is complete. There is no longer nervous anticipation or distraction, just complete immersion in the machine and the mission. Starting the F-135 engine, built by Pratt & Whitney, it is the most powerful fighter engine in the world, and feeling 43,000 pounds of thrust come to life beneath and behind you is, by all accounts, a sensory experience unlike anything else in human existence. The aircraft knows what it can do. The pilot must guide it. Siren's longest mission to date has been just under 12 hours, an extraordinary endurance feat that requires maintaining near-perfect cognitive concentration for the entire duration, managing fuel states, weapon status, threat environments, navigation, communication, and aircraft systems simultaneously for half a working day. Even with modern automation handling much of the informational workload, the mental demands are immense. Her closing reflection is perhaps the most resonant moment of the entire experience. She notes that she does not particularly think of herself as a female pilot or as the only woman among Lockheed Martin's F-35 test pilot cadre. She thinks of herself as a fighter pilot, full stop, and credits her colleagues for making that the culture of the team. But she also acknowledges the weight of representation, knowing that young women with aviation ambitions are watching, and that her presence in that cockpit tells them, concretely and undeniably, that it is possible. Not theoretically possible. Actually, demonstrably, presently possible. That is perhaps the most powerful weapon in any arsenal.